So here's a video reviewing section 4.2 by request. And section 4.2 is about maximum and minimum values. And this is where we learn the definitions of absolute max, min, and also relative max and min. And so let's just take a quick look, well, maybe not so quick of a look. Here's a definition from the textbook on or of absolute max and absolute min. It might be slightly different than what I gave you in the notes because, I pull my definitions from different sources than our textbook. So, but it has all the correct relationships that we're looking for. So if it's a little different, that's not that big of a deal. But the definition of max and min, or absolute max and absolute min, is exactly what you would think it should be. Absolute max is the highest output on an interval, and absolute min is the lowest output on an interval. And to make sure that this is clear here, actually let me use a better color. Notice that in doing this relationship here, I don't like any of those things. We can see that we have an or equal to sign in this inequality, as well as in this inequality. We have they're equal to. So as we saw in our notes that even on a horizontal line, we have an absolute max. If a horizontal line produces one output over an interval, then on that interval, that one output is the largest value. It's also the smallest value. And so don't try to overcomplicate what we're doing. When in mathematics, we try to take an idea that's common or should be somewhat common, and we try to put some precision to it so that when all of us talk about it, we all mean the same thing and there's no ambiguity to it, or at least we try to minimize the ambiguity. And so that's, the largest value. This is how we define it because, it makes sense mathematically. It's the highest output is the absolute max, the lowest output is the absolute min. And like I said, even a horizontal line has those things, as the largest output and a smallest output. And so they're still maxes and mins. Now let's contrast. I'm not going to give you, I didn't write out the definition for this one from the notes. The book's definition is more concise than what I gave you, but if you read this subtext below the definition, it gives you everything that I gave you in the definition on the board and everything we talked about. Now, relative extrema, the key to this is that a location, a value at C, say this value right here, is the location of a local or relative extrema. If I can put an open interval around that point, so this is my open interval around this point, such that the output at this point here is the smallest output in this for the local minimum or relative minimum. If that's the smallest output on some open interval containing C, then that point, f of C, is going to be a local minimum or relative minimum. And so if you notice, the interval I placed here around this point does give me the lowest output on that interval. And so this would be the location of a local min. Now, local max, if I put a, let's call this C sub 2 over here, if I put an open interval around C sub 2, and I'm just projecting it upwards so that I can show you that, at that point, on some open interval containing C sub 2, f of C sub 2 is the largest value, is a maximum, the absolute, on that interval. So as long as I can place an open interval around the x value and that output at that value is the largest or the smallest, then we have a local extrema happening there. Now, one key thing about the definition is that although I can put an open interval around A, and then this is the largest output on that interval, the function is not defined on that entire open interval, so we don't allow this place, or at A here, to have a local maximum value, because we want to make sure that the function itself is defined on the entire open interval on which we put around the x value. And since the function here, as given, was not defined for values of x less than a, we cannot let this be the location of a local extrema. Similarly, over here for b, we don't let that be the location of a relative or local extrema as well, because any open interval I put around b, or any open interval that contains b, will have values in that interval where the function is not defined. And if that's the case, then we don't allow it to be a relative extrema. So what we're trying to do here is identify points where we have a peak or a valley. In other words, it could be a maximum value or it could be a minimum, but on the given domain it's not the highest value and it's not the lowest value. But there is some interval on which I could make it the highest or make it the smallest. So it's relative or local in that area. And relative or local extrema, or important features of a graph that we're going to want to be able to find for application problems, for sketching curves and things like that. We want to know where those places are, and so that's why we identify them with a special name and work to find them. So moving on, we had the extreme value theorem. The key thing about the extreme value theorem, or EVT, was that if we had a continuous function on a closed interval, that's the condition right there. If we have a continuous function on a closed interval, then we have to have extreme values for that function on that interval, meaning there will absolutely be a max and there will absolutely be a min, and they're going to be an absolute max and an absolute min. So anytime you know that the function given is continuous on a closed interval, then you know that there's going to be a maximum value on that interval for the function, and there will also be a minimum value on that interval for that function. Now, if the function is not continuous on the closed interval, there still may be an absolute max. There still may be an absolute min. There may be just one of each, one or the other, or there may be both. What EVT guarantees for us is that if we know for sure it's continuous on the closed interval, then there has to be an absolute max and an absolute min. If for some reason the graph is not continuous on a closed interval, then there's no guarantees. There may be an absolute max, there may be an absolute min, there may be one or the other, there may be neither. Okay, the only thing we can guarantee is that the function is continuous on the closed interval, then there will be an absolute max and an absolute min. And then we got into critical numbers, and critical number, just to give you the highlights of this, C is in the domain of F, and F prime of C is 0, or F prime of C does not exist. Then C is a critical number of F. I'm going to abbreviate there because I'm running out of space. So the key thing here is that C, the function has to be defined at C. And then if the first derivative is equal to 0 or the first derivative does not exist, then C is a critical number for F. And one key point to this is the relationship between what we're finding here, F and its derivative. So if I'm talking about any function and its derivative, any function where its derivative is 0 or its derivative is undefined, then I'm talking about critical numbers for that function. And so if I have f prime as my function, and I look where f double prime is equal to 0, and where f double prime of c is undefined, then those values would be critical numbers for f prime. And I can take this up and down any level, okay? As long as I have a function, and I look at where the derivative of that function is 0 or undefined, then we're talking about critical numbers for the function that we're talking about. One of the big theorems that we had, I don't know, big, key, those might be too strong of words, but one theorem that we have is that if we know for sure f has a local maximum or minimum at C, local extrema at C, then we know C must be a critical number. So any place where the function has a local max or local min, then either f prime of C does not exist or f prime of C is equal to 0, guaranteed. Now the converse of that is going to be false. And the counterexample that we used to show this was, it's supposed to be a cubic, and this is occurring at the origin. I should probably change the color. If the origin was right here, roughly, then with the cubic, f prime of x, of course, equals x cubed. I'm sorry, that's not the one. Let me go back. F of x is equal to x cubed. f prime of x is equal to 3x squared. So we can see clearly that f prime is equal to 0 at x equals 0, and so 0 is a critical number. However, this graph does not have a local max, nor does it have a local minimum at 0, and so the converse of this statement is not true. Just because f prime is equal to 0 at some location or does not exist, we may have a local max or local min at that point. That's why we set up our intervals and test with the first derivative test, but we are not guaranteed a local max or local min occurring there. That was more section 4.3 stuff, where we actually looked at that first derivative test and then for relative extrema, and then the second derivative test for relative extrema. So go look at your notes for that if you want to recall some more specifics about what I was just mentioning. One of the last things that we dealt with, but not the last thing, was what the book calls the closed interval method. So if we're trying to figure out if we have, or rather, what are the maximum and minimum values for some function on a closed interval, rather, let me rephrase that, for a continuous function on a closed interval, we know by EVT that there's going to be a max and a min. The closed interval method is where we, find the critical numbers, and then plug those critical numbers, which I'm going to call C hashtag here, C numbers, and endpoints. We plug those into f, the original function, and then the biggest will be the max and the smallest will be the min. Okay, so if you have a continuous function on a closed interval and you're asked for the absolute extrema, not the relative, this is for absolute. So you're looking for absolute extrema of a continuous function on a closed interval. Then you take the derivative, find out where the derivative is 0, find out where the derivative is undefined, take those values, those are critical numbers, plug them back into f, and then plug the endpoints into f. And just look, which one's the biggest? That's the max. Which one's the smallest? That's the min. And that's all you have to do for that method. So if we wanted to do a brief example for that one, if we let f of x equal, if I make this up, we might screw this up a little bit, but why not? Let's try it. Let's say we have x e to the x. Whoops. Okay. So, and let's look on the interval from, and I'm just making this up completely, let's go 0 to 3. So I would take the derivative, and of course we have to apply the product rule here, so I get the derivative of x is 1 times the second factor e to the x plus the derivative of the second factor, which is e to the x, times the first factor x. Now this is never undefined, so I don't have to worry about that. I should write a comment to that effect to my reader, but I really need to figure out where this is equal to 0. So if I factor out e to the x, I get 1 plus x left here. And we know e to the x never equals 0. And so 1 plus x, of course, equals 0 at x equals negative 1. And I happen to find a critical number that isn't even in the interval given. So to make this more interesting, let me go back and change. Let's suppose this interval here was not 0, but let's suppose it was negative 2, just so that negative 1 lies in there. If the critical numbers I find aren't in my interval, then I got nothing to do with those critical numbers, and I would just plug in the endpoints only. But trying to make this a little more interesting. So then I need to plug in, let's see, my endpoints, f of negative 2. I'm going to plug that in a moment. I'm going to plug in f of negative 1, figure out what that is, and then I'm going to plug in f of 3 and figure out what that is, and then try to determine the absolute max and absolute min. This is going to be negative 2 e to the negative 2. This is going to be negative 1 or negative e to the negative 1. And this is going to be 3e cubed. I don't have to think a whole lot about the maximum value here. The maximum value is clearly going to be this thing over here. E cubed is going to be, I don't know, bigger than 8 and smaller than 27. It's going to be closer to 27 because e is closer to 3 than 2. And then times 3 again. So that's going to be bigger than these two numbers over here, which are both negative. The smallest, let's see, my brain is now freezing up for a moment. Let's see. This is negative 2 over e squared, and this is negative 1 over e. And you should probably run that through a calculator to see. I believe that this one down here, whoops, is going to be the absolute min. I'm just running this through my mind right now. Yeah, that's going to be the absolute min. So at this point I would just write a sentence and tell my reader exactly that my absolute min is negative 1 over e and my absolute max is 3e cubed, and that answers the question. I apologize for the sloppiness, but I'm trying to get this out later in the evening, and so people have it, and well, I hope it was helpful. Go study.